Good afternoon, professors and judges. We are from Ching Middle School. And today's our topic is about pseudo-Pythagorean triple generator for perpendicular median triangles. We start with finding a very interesting properties about a triangle with a pair of perpendicular medians. The side lengths A, B, and C must satisfy the governing equation a squared plus b squared equals 5c squared. And we find an example for the integral solutions of this equation, which is 22, 19, and 13. Therefore, we want to know whether we can find all the integral solutions of this equation or not. Therefore, we use programs to exhaust the first few results and find that most of them cannot satisfy the triangle inequality, as shown as here highlighted in red. Therefore, we want to add a constraint about this problem. And now the problem changed to find integral triples A, B, C, which satisfy the governing equation and also the triangle inequalities. With modification with theorem 1 and 2, we actually proved that the triangle inequalities are actually equivalent to A greater than C and B greater than C. Therefore, the problems will be modified into the following, replacing A greater than C and B greater than C by the triangle inequality. With these two inequalities, we can now eliminate out the undesired triples, and now we can get the following tables. And by looking at this table and the governing equation, it is easy to observe that A and B are symmetric. And also, if we want to find all integral solutions, we only need to find the primitive solutions of this equation, because we can always multiply the triples with integral multiple to get the others. And also, for primitive solutions, we can prove that A and B must have different parity. Therefore, in the coming project, we assume A is even and B is odd without loss of generality. And now we have our final problem, which is finding all primitive triples which satisfy the two constraints as said before, with A even and B odd.
Let me ask you, do you say you can prove that this is a sufficient condition for a triangle to be formed?
Yes. And this is a problem actually involves number theory and geometry. And we are inspired from the well-known Pythagorean triples in number theory. And in this theory, it talks about a Pythagorean triple can be generated by this generator, as shown here. And there is a nice property that all primitive triples and only primitive triples can be generated. Therefore, and also, A, B, and C will automatically satisfy the triangle inequality. Therefore, we want to do similar things on our perpendicular median triangle. Therefore, we modify this generator and gets our generator for generating our desired triples. And we define the triples satisfying the previous problems, call them pseudo-Pythagorean triples, or PPT for short. After simplifying the generator we said before, after eliminating out the absolute value, we got these two generators for corresponding boundaries for M and N. And we want to ask two questions about this generator. The first one is whether this generator forms only primitive solutions, and can all primitive solutions generated by this generator. However, in this table, we generate the first few results by our generator and find that some of them have a PPT of GCD equals to 5. Therefore, the answer for the first question is no. It is because apart from the primitive PPTs, we also find the other PPTs with GCD equals to 5. And we have theorem 3 to prove that the GCD of the PPT formed by this generator can only be 1 and 5. Note that the GCD of ABC can only be 1 or equal to 5. And for the next question, whether all primitive solutions can be found by this generator, the answer is yes, because we have theorem 4. Theorem 4 shows that when ABC is a primitive PPT, we can always find the corresponding ordered pair M and N. And now, if we still want to construct a bijection between the parameters M and N and the primitive triples A, B, and C, we should eliminate out the PPT with GCD equals to 5. Therefore, by observing the relation between the PPTs and their corresponding primitive PPTs, we introduce the following important transformation for the parameters m and n. This transformation is very important and very essential for eliminate out the PPT with GCD equals to 5. With this transformation, we can show that in theorem 5, if m prime and n prime are also relatively prime, then m and n can form primitive PPT. Therefore, this transformation can actually act as a checking method for us to eliminate out the PPT with GCD equals to 5. In this table, we can see that if m and n maps to a not relatively prime m prime and n prime, just like here shown in highlighted in red, it generates a PPT with GCD equal to 5. Otherwise, it is a primitive PPT. Therefore, with using this transformation, we can now generate all and only primitive PPT, satisfying the equation as said before. And this generator, we have compared the time complexity for this generator and using exhaustion for finding primitive PPT. And we find that the time complexity of using exhaustion is OR squared, and the time complexity of our generator is OR. Therefore, our generator can generate primitive PPT much faster. And later on, we want to generalize our findings from the side ratio of 1:1 to arbitrary ratio P to Q. And the governing equation becomes as follows. And after modification, with reference to theorem 7, we'll extend our problem to finding all primitive triples which satisfy the new governing equation and the new inequalities. And we also find a generator for finding these solutions in theorem 8. But this generator can only generate PPT with GCD divide Q lambda, not equals to 1 only. And also, we can show that by this counterexample, this generator cannot map a pair of Mn to a unique triples A, B, and C. Moreover, this generator cannot generate all primitive solutions. Therefore, if you want to construct a bijection, we should look at, here's some examples we generate from the computer. And if you want to construct a bijection, we want to look at a more specific case, say P equals T and Q equals 1. And then the governing equation becomes as follows by substituting P and Q. And we can see that the GCD of A, B, C will divide lambda. Therefore, it is natural to ask what happens when lambda is a prime. If lambda is a prime, then the triples will only divide 1 and lambda. Therefore, we should eliminate out the triples with GCD equals lambda. Therefore, we introduce the similar transformation from Mn to M prime and N prime. And actually, we can also prove that the GCD equals to lambda, the PPT with GCD equals lambda will also be eliminated. And this is an example when T equals 2, we can find some PPT with GCD not equals to 1. Therefore, by this checking, when M prime and N prime are also relatively prime, then we keep it. Otherwise, we throw it away. Therefore, we can generate all primitive PPT for arbitrary T, making lambda as a prime. So in conclusion, our paper have completely constructed a new generator for PPT of perpendicular median triangle. And we give rigorously proof that it generates all and only primitive PPT. That means a bijection can be formed between the parameters M and N and the triples A, B, and C. And also, it can generate PPT faster than exhaustion. And then we want to extend our problem to arbitrary ratio P to Q. And we find that when P equals T, Q equals 1, and when lambda is a prime, the generator still keeps the nice property that a bijection can be constructed. And thank you for listening.